Right. Thank you so much to the organisers for having me, and thank you also to the organisers for putting this on. The first two talks were great. I'm hoping for some really more exciting talks as well. It's really nice to be part of like a new conference, especially on something you care so much about. So thank you. Right. So I'm talking about my project PlasmaFAIR, which is about trying to make software in our community better. How to work out how to advance my slides. There we go. So I'm going to talk about what PlasmaFAIR is, and then some of the things that we've been doing. So PlasmaFAIR is my research software engineering fellowship from EPSRC. It's a 5-year project ending about June next year. It's about £1 million. That pays for basically my time and another RSE, Liam Patterson, who is working with me. And basically, the aims of the project are to try and improve software sustainability within plasma science, sort of broadly. If you say that you do plasma, then I believe I will work with you. And by software sustainability, I think I'm perhaps preaching to the choir here, this particular audience, but I mean the capacity for software to endure, for it to still work. The software is so important to the research that we do that I want it to be, the best that it can be. And instead of doing, a few big projects, a few big features on a small number of packages, I'm trying to do smaller, more focused projects on a large number of packages. So our typical projects are about 2 weeks to 2 months. Sometimes they're a bit shorter. I did something in an afternoon last week that helped somebody out, and some things are a bit longer that we've been involved in for years. These projects are free to researchers. My time's already been paid for, so I'm doing this stuff for free for people. And these projects normally start off with some kind of software health check. So you might have seen these sort of things before. This is adapted from the Journal of Open Source Software, JOSS. They've got this like reviewers checklist, so we've kind of built on that. And we're looking for things like, is the software fair? Is it findable, accessible, interoperable, reusable? Again, I think I'm perhaps preaching to the choir, so I wouldn't really explain what that means so much. Does it have good documentation? Does it work? Is it easy to install? Basically, how easy is it for an outsider to come along and start using your code, or to start like modifying it and building upon it? Our typical workflow on like a typical project, we'll go through one of these health checks, look at the code and the project as beyond just the software perhaps. We'll have some kind of assessment, sort of informal thing. We're not kind of giving people grades or anything. And then we'll discuss with the developer, the person that we're interacting with, about the sorts of things that we could do on that project, the sorts of things that they want us to do on that project. And typically these look sort of like what I've got on the screen here in this sort of order. So we'll do some work on the build system, typically as a first point. That makes it easier for us to get it installed on other systems. So we've done a lot of packaging of Python projects. This is something that I think we can really help researchers on, not because it's very difficult. It's actually quite easy to package a Python project, but it's really difficult to find out what the current advice is on how to do that. Like if you go search Python packaging, you'll find stuff that goes back 10, 20 years. And so disentangling that can be quite difficult. We've done this a lot. We know how to do this. We'll also build test suites. We kind of come into a lot of codes where the researcher has some basic tests, or they've got like an example, or they've got some workflow that they know works, and then we'll help build that into something a bit more automatic. Get linting on there, like look at compiler warnings, that sort of thing. Write and build documentation. We're obviously not going to be the experts on how your code works, but we can kind of get the framework in place, and then we can use continuous integration to kind of automate all the above things and get that so that it requires little manual intervention. And that helps just mean that the researchers can kind of step back and let this stuff kind of work automatically. Some projects will end up like refactoring or adding features. Um, so I'll talk about some of the like example projects that we've worked on and the sorts of things that we've done. And then we might get through some cycle of expanding the test suite, adding stuff, refactoring things, tests. And the last thing that's really important is that we hand it back over to the researchers so that we're not just kind of like changing their code underneath them and then kind of giving back to them, being like, "Here, we've done some stuff," but actually kind of ensuring that they know how all the stuff that we've done works, so that they can continue, like if they need to enhance the build system, add more stuff, and also so that they can take that knowledge from this project and apply it to their own future projects. So that they start a new Python package, for instance, they can look back at this one and they understand how it works, and they can apply that to the next one. So to go through a few projects that we've worked on, this one, Scotty, was a fairly early one. It's a beam tracing code for Doppler backscattering diagnostics in tokamaks. And this is a pretty typical project in that it started as a PhD code. It was developed for that single researcher, developed to show a proof of concept of something, and then it's slowly grown since then, and it went from like a single Python script to being a collection of scripts, or it might have been a collection of Jupyter notebooks in other projects. And now they've kind of got to the point that other people are interested in using their code, and it's being used to do like production physics in institutions around the world. Other projects might be that kind of got to this point where they're also about to publish a paper and they're being really good and they want to publish the code alongside the paper, but they're kind of not super confident in the quality of their code, and having us come in and kind of like giving it the thumbs up or kind of doing some work on like tidying it up gives them that confidence that they're happy to make it open source and publish it alongside the paper. So now Scotty has gone from like this bundle of scripts to being a package you can install from PyPy. It's got cleaner decoupled code, so instead of like one or two big functions, they've pulled apart into smaller functions that can be reused in separate places and that are more amenable to being unit tested. We also did some work that is kind of a bit trickier for the kind of average scientist software developer, say, in doing some like more complicated Git things. So there were some large binary files that had been committed, and basically the repo had ballooned up to like several gigabytes, which for a small Python package, is a bit incongruous. So we did some work to retroactively remove those files from history as if they'd never been added and reduce the repo size. And as is inevitable when you add tests to a project that had tests, we find some bugs, and so we fix those bugs. We found some easy performance wins, fix those as well. Another project we've worked on is Pyrokinetics. Barvin has a poster later today. It's poster 26, so I think that's in room A. You should go look at it. I'm not going to talk about what Pyrokinetics does very much, but basically it's a brand new community library for supporting like the pre and post processing of gyrokinetic simulations. PlasmaFAIR, we've been involved from the very beginning to help set it up and basically kind of help bake in best practices and sustainability to the project from the very beginning. So this was less about coming in and like refactoring something and making it better, but like helping the researchers that actually know how all this stuff, all the physics works, and how experts on the individual gyrokinetic simulators, helping them develop a Python code that ties all this stuff together, and that is as the best that it could be from the very beginning. So we've continued to be involved in that at a much lower level nowadays than initially, but yeah, this is so as well as working on improving existing codes, we help set up new projects as well. So my text is all over the place. I think I've rejiggled the theme and it's just messed up my text. Um, because we've got this overview of lots of different projects, we've got this like overview of the ecosystem of Plasma tools. So I asked a question in the first talks about GQ disk files, which are these really awful file format, several thousand lines, just like tens of thousands of numbers, very little metadata, really objectively bad file format, but they're everywhere. This is basically how we use distribute equilibria data, and so it's really opaque. It's really awful. Everybody wants their own like reader and writer for these, and so we've been working on Pyrokinetics, which had its own reader. And we also worked on a separate code, FreeGS, of which there's a talk going on about a FreeGS derivative in the other room right now. So that's a nice sort of synchronicity there. And that also had its own GQ disk reader. And also this other file format, a related file format, AEQ disk. And because we could see these separate projects because people were working on them, we pulled out FreeQDisk as a separate library, separate Python package with both GQDisk and AQDisk files in, and then we can add it back into FreeGS, back into Pyrokinetics, delete like the code that we had in there, and we could also add it to new projects like Scotty. So now Scotty can read GQDisk files just using this library, and also so there was another researcher that wanted to add the PQDisk file format into Pyrokinetics. We got them to add it into FreeQDisk instead, and now everybody can benefit from like this kind of new functionality. Because also we can see like we're working on all these different packages, and we've kind of got a bit of freedom to work on what we want to work on. We're also able to make improvements to kind of like the even wider ecosystem. So Liam made some fixes and features into F90NML package for reading Fortran name list files. And so there's like another 300 packages that use that, outside of Plasma physics that we've helped. I did some performance improvements to Fortran format, another tool for reading, writing Fortran text format files. And there's like another 100 packages that we've benefited from, our work and being able to see like the whole ecosystem. So we've also done work kind of further outside plasma science that benefits people inside plasma science. So we've heard NetCDF a couple of times already, which is a file format, if you don't know, that's quite widely used in our community. If you build the base C library in debug mode, it turns on some compiler warnings and spits out about 2,500 compiler warnings, which aside from one thing was like slowing down the build just to show you these warnings. But also means that like if any of these warnings are actually serious, they're just completely lost in the noise of all these different warnings. So I did some work to go through, fix these warnings as many as I could. We've got it down to so they've just made a new release, and now there's only about 100 warnings, stuff that was just like too complex for me to fix, or maybe actual bugs, leaving that to the actual developers, maintainers. And yeah, so that there's that, and then also you may be aware that NetCDF doesn't have native support for complex numbers, and complex numbers are not used like massively, but they are used quite a bit in our community for like eigensolvers, for instance. And every code that uses complex numbers and wants to save them into NetCDF has to come up with basically how are we going to do that. And so there's a bunch of different conventions for how to actually store complex numbers in NetCDF files. And the maintainers in NetCDF were kind of like umming and ahhing about how they're actually going to get it in there, and they were taking some time. So I developed NC Complex, which is a really lightweight extension library that sits on top of NetCDF and converts to and from programming languages native complex number types to the several different conventions inside a NetCDF file. That's now available in the Python NetCDF package. So if you use that, you can open data sets with auto complex equals true, and that will basically automatically read and write complex numbers for you. The last thing that I want to mention is kind of moving even further away from plasma science, but still benefiting people in plasma science, is that a lot of our code is still written in Fortran. We really like linters that tell us like extra warnings that the compilers might miss. There are a bunch for Fortran, but they're either like unmaintained, very slow, or just quite difficult to use. So Liam started writing one just as an internal one, just for like one particular project, helping like find and replace like certain patterns. And now this has grown to Fortitude. This is now used by several groups all around the world. The Met Office are using it. We have, I'd like to say it's inspired by Rough, the Python linter, which you may be familiar with. We've actually completely ripped off Rough. We're using a lot of their code. We just swapped out the Python bits for like Fortran bits, basically. And this thing is quite fast. It can check 51, 52 rules and about 250,000 lines per second. So if you write Fortran, check out Fortitude. Okay, that's my time. I just want to plug PlasmaFAIR, plasmafair.github.io. If any of this has interested you, we're looking for more projects. Drop us a line. There's a form you can fill in. We've worked on more than 30 packages. We've helped more than 100 researchers. We'd love to hear from you. We would like to help you. Thank you.
Great. Thank you very much, Peter. I think we have time for a couple questions, and there's a couple in the chat that I'll start by reading off. So Remy has asked or said, code shyness is a real problem in my opinion. People waiting for their code to be perfect before publishing. Spoiler, it never is effectively holding development and collaboration back. What can we do to mitigate this shyness?
Yeah, absolutely, completely, 100% agree. Partly, this is what we're trying to do. That like with the health checks, come in and like look at researchers and code and tell them basically it's fine. Like almost everybody says like I'm not a software developer. My code is awful. I always tell them your code is basically average. It's fine. Like I've seen code much worse than yours. It's fine and it's good enough. I think that's it. We just need to kind of convince people that it's good enough. It's fine. Get it out there.
Great, thank you. And then from Emily Bourne, have you had any pushback from codes that don't want you to suggest improvements?
Yes. And then we don't do anything for them, basically. Like the people, it's a little awkward in that, we end up doing projects for the people that care about their code. And really, I'd love to do projects for people that didn't care as much, right? But that's much harder. So I'm hoping sort of partly like a network effect. We lift up everybody around them, and then they sort of feel peer pressure into like making their code better. Some people, we suggest lots of things and they don't want all of that, and we just kind of scale back our ambitions and kind of do a little bit. And some people are just kind of outright no. The biggest problem I think actually goes back to Remy's question, that we've dropped lots of projects. We've just kind of run out of time and not done anything because people wanted to get their code in a good enough state for us, the people that want to make their code better. That has been the bigger problem, I think, that people just saying no.